I think I will make use of our remaining time today to briefly walk you through some important derivation of the topics we cover in the course. Of course, we here we put strong emphasis on paper presentation to help you get the intuition, right? But for a more formal note, I would like to also give you a wrap up beside the let's say the presentation beside intuition. I want to show you, let's say, the form, the technical terms, so that you are not afraid when you see them later in the papers, right? But basically, we are familiar with the terms themselves when we read the papers, but what do they really mean? What impacts they might have, right? And so yesterday I stopped at the the threat to internal validity, right? And so basically, we want besides the unbiasedness, we want to make sure that our estimators is consistent, right? That means it do not vary over time. And that's why we put a strong emphasis on the inconsistencies of standard error. If the estimators are unbiased or consistent, the standard errors may be estimated inconsistently, right? And there are two sources of inconsistency. The first one is the heteroscedasticity, and next, the autocorrelation. What do we mean about that? So you see that for most of the paper we have, the authors use robust standard error, right? And robust here means we try to solve the problem of heteroscedasticity consistent. And under the assumption of heteroscedasticity, each data point follow a different types of distribution or even the same distribution but with different means and standard error. And so that make our estimator not efficient, right? That means they do not have the smallest variance. And in the previous note, I have shown you two very simple case, two simplified case where we have one robust or one unbiased coefficient and one is pretty biased. But the biased one has strong or has low variance, right? So we researchers have to face a trade-off. What do we want to, let's say, to focus on? Sometimes people think that having a proper unbiased estimate is good because it helps them make precise policy. But for some other researchers or policymakers, they think, okay, I don't mind if my coefficient is a bit different than the true one, but still I know that in most of the cases, maybe in 95 or in 99 of the cases, my estimator with different types of data set will lies in between this range, and this range is relatively small, so it's okay, it's acceptable for me. Then we have the second source, which is autocorrelation, or we call it serial correlation. What does it mean? So error terms are correlated across different observations. And remember, in some cases, we see that some error terms are correlated because they belong to observation in the same zip code, right, or within the same year. The fixed effects to some extent capture the time invariant, but still the error terms captures the unobservable ones, right? Unobservable characteristic that could be solved with fixed effect, And once it is in our error term U or epsilon, there is still correlation. So random sample excludes autocorrelation because we are confident that we randomly pick the sample from our population, that's okay. But how about the case that maybe for one survey, right? The survey data, they are not random because first, depending on the groups of people, maybe someone who wants to get some pocket money, they come to us and they are willing to conduct the surveys. And second, maybe if we conduct a survey in, let's say at VGU, it's highly probable that we interview the students or the lecturers or the employees at VGU or BU area, right? So if we, or even closer, we could narrow down to that area, right? And that means we could not generalize the result for maybe people in Ho Chi Minh City, right? Big Ho Chi Minh City, comprising the former Ho Chi Minh City, BU, and now Vũng Tàu, right? And so for the types of correlation, we face that in time series data, we see that a lot, and heteroscedasticity consistent standard error will be inconsistent. And how about the external validity? We cared previously about the internal validity. How could we, let's say, conclude that our sample, the estimate we have from our sample could be generalized to the population that it's representing? But here, for example, the external validity mean, okay, for this one, how can we generalize that for a totally different population in other countries, maybe different time or different institutional setup, right? Maybe the results for bank lending or relationship lending might be different than the one with, or let's say bank-based is different than market-based institutions, right? And also with experimental context, if we test it on, let's say, mice, how can we make sure that it will be applicable, or let's say it's also valid for the case of testing in human, right? Without really testing that, then how can we make some, let's say, proper or confident claim that, okay, it works for mice now, it's highly probable that it worked for me, right? So it's about externality. And then most of the time, what we could do is to mimic, to replicate a paper in a different context, like the same setting, the same set of variables, and even the same like number of observations, the same years, right? But still, probably we will obtain different coefficients and different standard error, right? And that answers that modify our interpretation, or probably in another setting, we have other confounding factors, unobservable factors that distort the result. Then you see that the paper, most of the paper right now, they do not simply show the effect, but they push one step further to find the mechanism, right? From A to B, we know that there is effect, but what about the mechanism? What about the channel, right? For example, if I know A leads to B, but probably they are going through some other channel like A to A1 and then to B, and when you read some paper with the terms moderating effect or moderation, then you will see the link, how they show the effect goes from one to another. That's the models, like researchers are trying to prove that they do not simply show the result, but they really want to show the mechanism, right? And internal and external validity of the forecast, if a regression model is used for forecasting, right, it's not really that important that our model estimate the causal effect. Why is the case? Because when we try to run regression to test some policy, right, maybe the establishment of IFC in Vietnam or the effect of collapse of Lehman Brothers, that is about, let's say, to find the effect of some policy or some event. But in terms of forecasting, still that we want to make sure that to some extent, if we identify the proper, or we could predict the proper data generating process, we know the mean and also like the path of our coefficient, then maybe we will tolerate, we allows for some, how to say, some consistent, some inconsistency or some discrepancy, right? And in fact, so from my experience when I work with prediction model for trading companies, so it's not really about finding the correct effect or to make the correct prediction, but we want to know if the model is useful enough. So far we have learned that maybe it's just our joke, but there is no correct model, but indeed there is useful model. What do we mean by that? So some model might work very well in stable time, and some model may work much better in crisis time, right? And some model, let's say in terms of electricity price prediction, some model are very good at predicting the price during the day in the summer, right? But for other model in the winter, we need to fine tune it. Maybe we need to assume a different dynamics, and usually that's where you have to incorporate different types of training in which you know you need to get some, we call it the know-how effect. We need to know like the knowledge domain, right? What happens with the input and what is the expectation about the form of the output. So maybe for some bank, they are quite specialized in providing loans for corporates, right? But some banks, they are also specialized in providing mini loans, we call it the microfinance for people. Of course, it will be a smaller size, shorter duration, but the risk now is spread, right? So instead of spending maybe 1 billion for just one company, I will now split it to 1,000 or even 100,000 mini loans for different types of small borrower. That might be, how to say, students, right? Or parents that need some short-term financing to cover their family, or maybe in their peak of debt holiday, they need some short of liquidity and they just need that small amount of financing. And now for the same amount of money, the risk is spread across different or multiple individuals, right? And if someone failed to pay, I still got it covered by another one, or to some extent, I know that my value as risk, in the worst case, that I could get some value back. But if the company is borrowing my money and if the company went bankrupt, it's less likely that I will get the expected amount of money I want. So it's about, let's say, the purpose when we run regression. If that's about forecasting, then we might not put strong, let's say, focus or strong motivation on finding causal effect, but we want the model that worked well with different dynamics, or that give us a, we call it like the usable and acceptable results, right? That might not be really correct, but it could predict the movement, right? And any variable that helps to improve the forecast is useful, even when it's not causally related to the variable to be explained. And for forecast, please keep in mind that it's crucial that the estimation has to be first high explanatory power, right? And then it has to be precise, and the results of the estimation can be generalized to other population. And that means now external validity is more important when we do the forecasting. few examples for that. And probably in the exam, I will have the example, and you could write down like your line of talks, right, about what's going on, how do you interpret the data, how do you guess the confounding factors. For example, here we want to predict the score based on the expenditure or education training, right, education spending. And that might be the case that the income, right, or the ability, we're so familiar now with the ability variable that could drive confounding factors because it affects both expenditure and affect both the average score and even the income of the family, right? Let's say if you are luckily born in a family with like wealthy background, then probably you are more likely to spend higher level of expenditure on education, and in the end, or as the result, you will get higher score, you have better performance at school. But how about how to assess the internal validity of our study results? Yes, so we argue that there might be omitted variables, right? Average income or the poverty rate in the school district, probably, for example, school in low-income residential area, they might attract different types of household, and that also affects the lifestyle, the spending, and in the end, we may see reflection in the average score of the student or of the children. I will just skip them if I think we already covered quite substantially in class. It's about the bias, right? And we want to know that, okay, what is the direction of the bias? So in case that we have the omitted variable average income, right? And we right now we assume that the coefficient of beta 1 is positive and significant. That means here, expenditure leads to higher average score, right? But in the presence of our income, how will beta 1 change, right, with the new, let's say, assumption of the missing or omitted variable? And if that's the case, then we assume beta 1 is positive and significant. And second, there is a positive relationship between average income and education spending. So now our omitted variable and our independent variables are positively correlated, right? And how does it change our beta 1 coefficient or estimate? Then average income is likely a determinant of average test score, so it has positive effect on both y and x. And then we expect to see a bias, right? And when we so the average income both has positive effect on two variables, the y and the x, so it's pull up the level, so it inflates our beta 1. So the omitted variable average income will lead to the positive bias, right, in the estimator of beta 1. So when you run a regression, you might see that if we forgot to include x2, then the estimated value for beta 1 will be higher, right? Alright, so here I just show you like different scenario where it might lead to positive or negative bias, right? So very much depending on the direction and the effect. So if let's say correlation between x1 and x2 is positive, right, and our beta 2, like the effect of the true population is positive, then we may have a positive bias, right? That means our estimated beta theta is higher than the true one. And it's the other way around. If we expect to have a positive effect, but now the correlation is negative. That means the omitted variable pull down our estimated, so we will see a negative bias, right? So identify some direction or some sign of coefficient might help us in, let's say, explaining um, the relationship and try to push further to think if our operative variables make sense in this case, and this one is super special if we want to find the effect of our, or let's say to create one reliable instrument, right? Because instrument now has to create like a exclusive channel between our instrument and our wire, so the direction of bias play a role. And how about the poverty rate? So if both the coefficient beta 1 still significant, that means more spending leads to higher score, but poverty rate is negatively correlated, right? So when the poverty rate is higher, then the spending tends to be lower, right? So correlation between X1 and X2 will be negative. And then it might lead to, so because the poverty rate is already negative, so beta 2 is smaller than 1, and we expect also bias in beta 2, but now if we forget to include poverty rate in our regression, in our functional form, it will lead to the positive bias in our beta 1, right? So I think for those stuff, you could check it home quickly. I will skip it. And for example, like it contains lots of mini example, but all in all, it's for your understanding of the setting or of the techniques, right? Okay. Yeah, previously, for the beginning, we cover the importance of identifying the correct functional form, right? If you forget something, or let's say if you forget to take the log, if you forget to include variable, or even if you forget to capture the diminishing returns or the diminishing effect of one variable, it will lead to the wrong estimation of all of the data, right? And therefore, the choice of variables to include in the regression, in what form, is often at the discretion of those conducting the analysis. It's right up to us to identify what is correct, what should be included, right? And but there are some guidelines. The selection of control variables should be based like right before that, so priorly before the analysis results are shown, and it should be based on our economic consideration and theories. And variables whose omission that lead to bias should be included anyway. If we could find a proxies that is good, otherwise we have to use an IB to really isolate or extract the good variation. Otherwise, we cannot really claim that our effect is unbiased or this extent is reliable, right? And at the same time, if we try to include too many variables in our regression, it might have some negative effect, right? We know that the more we control, the higher the value of R squared, right? Even if we control for, let's say, autocorrelation, we use robust standard error, analyze, you cluster at different level, but still trying to include lots of variables might not be that helpful. It even create extra confounding factors because now your newly introduced variable are more likely or uh, abroad to be related to not even your Y but your X, right? Or if it's related to some other missing factors in the U, then you still face some severe consequences. And so adding irrelevant variables to a model, right, does not bias the estimated coefficient, but it will increase our variance and potentially it will lead to incorrect conclusion about significance, right? That might be the case that now your coefficient are no more significant, then you may see that, okay, there is no effect, but indeed, the effect is there, right? And just because we try to include irrelevant variables, and that's why I strongly recommend you whenever you try to include some variable, describe why you want to include that. So probably it's the theory that predicts that maybe the size of firm age has an effect, or if we see some other papers of the same setting, they include that. You also say that, okay, you are trying to apply the method, but otherwise, do not just simply include lots of variable until you find significant one, right? Because that is alpha seeking. And one of the easiest way to see is when the reviewers ask you to control for split variable, to drop some variable, or to split the sample. You are more likely to see the the consistency, right, is not there. Sometimes you see the effect is so large but insignificant. Sometimes it's smaller but significant, and therefore the results are not consistent across different specification, and then that will be a super negative, let's say, it's a minus to your paper when you could not defend the results in front of the editor and also the reviewers, right? So be very cautious about that and be explicit about what you include and why you include, right? Okay, so here I have a quick overview of the type data, but I think so far you are also familiar with the, let's say, time series, the panel, and the cross-sectional in other courses, so maybe you do not need to focus here, right? So remember the case yesterday when you have the survey data conducted in Vietnam, right? So probably if we want to use all of the observation, it is not the panel, but it's indeed cross-sectional. That means at each year we obtain different samples of people, right? And we could not really trace, or let's say one person do not show up throughout all the year of the sample, and therefore it is hard to or sometimes if you really want to use the panel data, then you will face a reduction in the explanatory power of your results. So one safest way to do that is to keep it as repeated cross-sectional data, right? And then we still have some way to work with that. Okay, so here panel data with time invariant unobserved heterogeneity, we could really rule them out, right? Age or cone effect with the fixed effect, or we could have like a random effect, right? But one important problem with panel data is the panel attrition. So that means that refers to the scenario when the composition of the panel does not remain constant over time, so the number of subjects that be reduced in spite of the resampling, something like that. So we need to, before conducting any test, I recommend you to first explore your data, try to see how they distribute, how they, or let's say whether there are some specific groups of your data really drive the result. Sometimes when you see that one subsample or one group that dominates the entire, let's say, sample, for example, maybe if it accounts for 60 or 70%, then there might be some source of selection here, or you are missing significantly information from the group that are left out, right? Yes. So for example, if some firms they went bankrupt for some year and they disappear forever, right? Or merger of firm, let's say A acquired B, and B will disappear in our panel data. But in fact, right after the acquisition year, now B is still there, right? But it just now under the umbrella of A. So the two firms, they combine the dynamics. There's some extra synergy. So if we make a conclusion just about firm A, then there might be some problems. Or for the case of leverage buyout, when some private equity groups, they try to borrow money from the banks to buy company from the stock exchange, delist them, make them from public to private firms, and they change the structure of the firm. So the entity, the type entity changes in this case, and therefore if you want to make some prediction or some conclusion about the effect of public firm, for example, then we will see that we skip one important dynamics, that that specific firm switch the status from public to private in some years, right? And in general, the more data, the better, the more observation, the better. But again, what is even more important is that if we have a small data set, but if we could prove or we could show that this small data set has quite similar distribution of the population, right? Then you could to some extent convince people, but otherwise, when people look at a study with small number of observations, then they always have some doubt, some concern about the validity, both internal and external validity of the results. And of course, different type of question requires different type of data, right? Sometimes you really need to use micro data to look at firm level or individual level or bank level, but at some point when your focus is more on the macro one or the effect at country level, so you could, let's say, iterate them at zip or country level as the bank lending yesterday in one paper Rabbi Yoko presented. If we look at just bilateral relationship between two banks in two countries, then maybe summing them up or iterating them at country level might give us a more general insights, right, about the bilateral relationship between the two countries. So that very much depends on what question do you want to use and what type of data, what type of model you are going to use to answer such a question, right? And then you have to depend on specific type of data. Okay, good. So I think that's it. And how about a functional form? I think for those, let's say, interpretation, you could work on it at home. Create at home is quite straightforward, right? And we are also familiar with those concepts when we read the model, when we discuss the model, right? And even the interaction term, why do you want to do that? And what is or what do each coefficient in the set of interaction term tell us, right? Here, so I already mentioned in the causality slide, so maybe we do not need to make strong attention here, but yeah, this one is how we are trying to visualize that, right? For example, we have this model beta 0 plus beta 1x, beta 2z, and beta 3x times z, right? And the bias will occur as long as our beta 2 is different than 0. And that means both of the lines will have different constant. That means we have different intercept here, right? And beta 0 here, and for example, beta 2 will be something extra, something on top of beta 2 when our line for z equals 1, right? So if z equals 1, we have in total 3 terms, right? Beta 0, beta 1, beta 3, right? And then that means the slope right now with z is indeed beta 2 plus beta 1 plus beta 3, right? And the coefficient now is beta 2 plus beta 0. If we ignore z, then the two lines, like if we forget to include z, then we are forcing the two lines to meet exactly at this point, right? And this is what really creates a misconception about the dynamics of our variables. So let's say if z is 0, we get beta 0 plus beta 1 plus epsilon, but z is 1, then we introduce in total 4 terms, 0, 1, 2, and 3, right? And that really shows us here on the graph. And so maybe in the exam, I will give you and then you help me identify what represent what, right? So which point represent the effect of beta 3, for example, which like it was Z1 and Z2, and these are, I must say that very intuitive and relatively, it's not that very much abstract, right? So you could have a look later. And also in the exam, I will cut some regression table and ask you what does it mean. That could be like this, like what is the, so I might ask whether education really has an effect on income, right? Why? Because yeah, here we see a statistically significant coefficient, right? If it is significant, then you cannot conclude that education has an effect. And then what is the magnitude, right? How large is it? So let's say 1 extra year of education relate to 11.03%, right? Higher income. But again, do not forget one very big or very important assumption, that is keeping other factors constant, right? Centristic variables, always use that in your, let's say, whenever you conclude about the effect. So here we control for a set of, let's say, a list of extra variables. So we take into account the gender, the sex of the individual. Right. So for example here, now if we take into account the interaction term, we take into account the female, the gender variable. If we take the marginal effect of education, basically we're trying to take the first derivative, right, of income on education. We will have beta 1 plus beta 0 female, right? So our marginal effect depends on the gender. So if beta 1, if female is 0, then we have beta 1. But if female is 1, then the coefficient will be beta 1 plus beta 4. That means now the slope of the two lines are very much different for the two groups. And here, right? So we have the interaction term, education times female, right? That is 0.0269, and it is statistically significant. But let's say what is the effect for a variation for an average female, right? So for an average female, that is think we do not have the battery in the same size. This one is much smaller. The way it works? No.
The big one.
Yeah, so you get this big one, and this is small one, right?
Yeah.
Maybe one is enough.
TV sana.
Okay.
Yes.
Okay, thank you. But remind me of like back to you.
Okay. Okay.
No, it's not working. Okay. I think this one rechargeable, right? Just because they are not consistent. So maybe the battery two times. This one is rechargeable. You only have one piece,
Yeah.
right? Okay. And I guess probably you need two, otherwise. But this is okay then without the camera? Do you think I think we still hear it quite well?
Yeah.
Yeah.
nose with
Yeah.
nose, right?
Trong-
So I'll upload that onto Moodle
Yeah.
so that you could check that too. So I think it's a problem with this one, right? Because usually when you click on it, you
Yeah.
see the green light.
Học miết tới 1 giờ.
Đúng rồi, maximum là 1 giờ.
Lúc nào xong nhắn chị cái chị qua lấy máy nó qua chị lên mà bảo phải đóng cửa.
À dạ dạ.
À là hôm qua là bảo vệ cửa hay là gì thì không lấy được cái chắc là thế này em biết bị hơn rồi quá.
interaction table, right? And that's another way that we could show the coefficient. For example, here is the coefficient of our female and male, right? Male means female is 0, so we have the education variable coefficient is 0.0991, which is E. And then female we add up, right? In this case, the difference between this point and this point is exactly 0.0269, right? Representing the difference between male and female for the same level of education. And for example, here, when we see that H1, H2, and H3 representing poor, fair, good, and excellent, here we do not have poor, right? Because we assume that poor will be captured by the constant, right? We have 4 groups, but only one group is captured by the constant. The other will have their own representation. And let's say here, it is good, 0.2904, right? So that is here. And this one is 0.991. And what is the difference between this red point and this red point? That exactly here, right? So the good one, the good category compared to our base group, and base group here is the poor, right? So this is the base group, this is the good. So the difference here what else do we need? So for example here, these are the interaction term, right? And if is the effect of education and income statistically significant for someone with a fair health, right? And what is the interpretation? The effect of education on income is always significantly positive. Basically here we see positive effect for all of the 4 groups, right? But it does not differ significantly between the health status. Basically here the difference between the 2 groups, it is insignificant, right? So we could not say that the 4 groups or the difference between the 4 groups are statistically significant. The difference looks like very small and also very insignificant. So that those are just extra illustration about the coefficient, right, for different level of age. And here we look at how the coefficient changes when we introduce the interaction terms, right? Not only education, but also, the square term, education times education. And we see that it's becoming very much steeper, right? Because now our first derivative depends on also the level of education. So if we have only one education, that might be flatter, but with the square term, quadratic term, then here it sharp increase the higher the years of education is. So basically that's it. And how about the next one? I think we already got some idea. That's me now when we check the data on the derivation, we will feel more confident with this one. So if you have time, so please have a look at like is how to say the way we could write our argument for causality, right? Here I give the sample of Goldsmith 1991, finance and growth. They tend to be a reverse causality, right? One expression is the causal relationship between financial development and economic growth, and how you frame or how you explain that there is potential reverse causality. So can economic growth be raised by improved financial institution? That means now if we increase the growth, increase the financial institution, then we see the increase in growth. Or the development of a financial system itself is just a response to the growth, right, to the economic development. So we have the reverse causality. And so far, if we want to find, let's say, causal effect instead of correlation, we should have identification strategy. Right? Yes, so we will introduce the empirical model, right? And the result here, GYB effects on our private credit to GDP, right? We see that the coefficient is 0.032, 3.2%, and it's statistically significant 1% level, right? We have to translate it to not only statistical significance but also economic significance. Basically, how, or let's say, what is the effect if we see an increase of our external by 1 standard deviation, right? So it was previously 3.2. It means increasing GDP by 100 percentage point increases GDP growth by 2.3 percentage points. This is our statistical numbers, right? But in terms of economic, we want to know if the number here is or has some real effect or some economic effect for that specific sample. That means now we need to check the standard error, or let's say the mean and the standard error for the specific variable. For example, here, for 1 unit change in our GYP, right, per capita GDP growth, right? We know that 1 unit change in the GDP growth, we expect, or it is associated with 3.2 percentage point increase in growth. That is statistic, but how about, let's say, what is the realistic, right, interpretation? What is the magnitude in real terms? Then we need to check. What if we push primary from the average value, right? So the average, as I said, when we run OLS, we do not focus on one specific firm or bank or unit, but indeed we try to find the average effect for the average person or average firm of the sample, right? And what if we push primary from the average value of the very slow moving country to average value of very fast moving countries? So basically we are trying to jump from here to here, right? And that is 22% increase in private, right? And we need to multiply this delta by our coefficient, right? So 0.22 times 3.2%, and that leads to, let's say, 0.704 percentage point per year, right? We have annual data with firm and year per 3 years. So we interpret the number is that the effect per year. And if it's but also in real magnitude is also very large. So 23% accumulated over 30 years, right? And let's say with the actual growth difference between the groups, we have 5 percentage points. Then 0.704 divided by 5 is almost like, let's say, 14%, right? So it's good. So for the other example, you are encouraged to read it at home, and I will cover next the annual fixed effect. We cover a few slides, right? Sure, yes. Okay. So for panel data, we have the observations for one unit across the year, right? What we could do is to find the fixed effect estimation. We could find even the first difference, right? Because if we do the first difference, T1 delta equal to 1 minus T minus 1, then what is time invariant will be cancelled out, right? And if we use the fixed effect estimation, we could use either the within transformation. Basically, we subtract each observation by the average. And of course, for the time invariant characteristic is constant over the years, the average is exactly the number, right? So if we subtract that, it's the same. And or we could use W variable as I said. If we have numbers of years and number of, let's say, areas, we multiply them and we have W variables for each of them. And that plays a role in capturing the time invariant characteristic of that specific year or year unit, something like that. And of course, they should lead to the same result, right? Because basically we are just applying different, let's say, processing, or we just change how we estimate that, but the model is the same. And if we, let's say, for the key for identifying cause and effect, we to control for objective variables, if that's observed, or we could observe that, always think of including them in our regressions. But otherwise, we try to fix that with IB, right? Remember, IB could be with almost like all of the problems we have in OLS. In the short slide, in the causality slide, I mentioned what's that is OBB, right, multiple bias, reverse causality, and the third one is the measurement error, right? Or even with the selection, we could be with that too. For the official slide, I show you 5, but yeah, in general, we have like 3 main ones, right? And if we do not have a valid instrument, we should look for some alternative. And here, using the fact that we have the panel data, 1 unit across the years, over the years, then we could observe like, let's say, so the factors are observed repeatedly over time, right? And for example, here in this graphic, it just answers the question if like how is the relation between beer tax and fertility rate, right? For let's say for the share of heavy drinkers on the fertility rate, we expect to have a positive impact, right? If you have higher beer tax, this may discourage people to drink, so we should have a negative coefficient. But a policy maker may react to it, and they will increase the beer tax if they observe high share of heavy drinker, right? So we also expect a positive correlation between share of heavy drinker and the beer tax itself. Here for like we should be very careful to Besides, if we use the panel data or repeated cross sections, right? Because indeed, panel is much better because we could have N and T, and we assume further that for the number of subjects in the cross section is large and the time dimension is small. Like we have for example 6 ways of survey, right? In Vietnam for the household, but for each wave we could have like in total maybe more than 5,000 let's say respondent. But for banks and firms, data one, we decided to trace their behavior. We may have just a small set, maybe just 200 banks, but we could cover we could have the coverage over 20 years or more, right? And it depends on whether we have large N or large T, that we could derive the asymptotic or linear distribution, right? And the asymptotical analysis runs through N, not T. So basically, if we apply the law of large number and the central limit theorem, so it's more or less, let's say, sensitive to N, not with T, right? And let's say under this condition, we could ignore the problem typically for time series analysis. So we know that the asymptotic behaviors are not sensitive with T, so we do not care very much, or we are not worried that much about the case of non-stationary or spurious regression, or we need to find the unit rules, right, for that. So here, panel of repeated cross section help us to some extent alleviate the concern of, let's say, threats from time series, right? And let's say we have, for a simple case of 2 N individuals, but only 2 periods, 1 and 2, right? And the individuals, households, firms, or countries, they are different with regard to many characteristics that are probably unobserved, right? And if you do not control for these factors, there might be omitted variable bias. And the main advantage of panel data is that we can relatively easily control for time invariant unobserved characteristics. For example, here we have delta 0 times delta 0 times d2t, right? And delta 1 x, y, xit, and the error terms. So the error terms now, DIT include, let's say first, time invariant effects, that is our AI, right? AI will capture all observed and unobserved time invariant factors. And other one is the actual idiosyncratic error terms, the error terms without any time invariant factors. Basically, we're trying to split the error term to make it time invariant and time variant one, right? And if we do not have panel data, we simply just have observation. We cannot identify if this observation comes from year or which year or which person. Then we run OLS. In that case, we have the pooled OLS, right? We cannot identify the T and the N or the 2 dimensions. And what if the OLS, the pool OLS works here? Let's say because A and U, from our assumption, the AI, right, that is the fixed effect or the time invariant characteristic, and U must not be correlated with XR. Is it plausible? It's not plausible, right? It's not the assumption is not implausible for only the U term, but for AI, for the time variant characteristic, they will correlate it, right, with the explanatory variables. Why? Because this fixed effect of the person, right, and that is, we predict that it will be highly correlated with our explanatory variable X in our, let's say, example here. In most of the cases, we cannot proudly say that AI is uncorrelated with XIT or D2T, right? And that's why if we insist or there's no way for us to identify which, let's say, observation for belongs to which year or which individual, we will have a biased and inconsistent estimator, right? Let's have a look. So we have like Y1, Y21, and we just apply the model in the first difference, right? Because now we have only two periods, T2 and T1, right? And then delta is delta Y is exactly delta 0 plus beta 1 change in betas and the error terms. And by doing by applying the first differences, all of the time invariant here, AR, right? We use subtract them, so it disappears, right? And if it disappears, then we could estimate using the OLS, right? And the parameter beta 1 can only be estimated if XIT varies over time for at least one individual. What do I mean by that? So that means we need some variation. So if delta is consistent, it's a straight line, there's no way for us to run a regression, right? Because we do not have variation in both x and y, and we could not measure beta 1 here. And by using the first difference, we already subtract the number of observation, right? And it leads to unbalanced panel. We lost a lot of data after missing value, and we also have high standard error, right? Therefore, usually it is not quite recommended to run it. What we could do is, for the same principle of the fixed effect estimation, we could use within transformation. So, for example, for all of the observations of the individual, we find the average, and we subtract all the points belonging to this person from the average, right? And then we have we calculate the deviation of all variables from their individual specific mean over time. What we can do is to, or we could use another alternative approach, is to include dummy variable regression, right? But again, if we include lots of dummies, we will lose the degree of freedom. For example, here we find the average over time, and with this information, we subtract YIT minus YI bar. Here, remember, YI bar, we do not have T, right? Because it's already averaged out over the years for this person, so only YI bar, right? And if we do that, the fixed effects already disappear, right? Due to our within transformation, and we call it like the DA, right? DA approach. We, or it is time DA data. And so the question is, fixed effects estimator or within estimator, right? For the estimation, we do not use the difference in the level of y across individuals. We use the deviation from individual specific needs. And again, so for this, we do not assume further the correlation between AI and XIT, right? Let's have a look at a few visualization. Here, so for example, I have time in variable sex, right? That can be estimated, so we create a for that, or time, right? So, for example, for each years, they have different dynamics of the macroeconomics, so we could represent that with one dummy capturing all, let's say, effect in that year. So basically, we could add a dummy variable for each individual, regression. So the number of parameters to be estimated is very large, right? We have n plus k. So k here is the number of like the variable, right? And for the estimation, we need at least 2 point in time. Otherwise, the W doesn't work because we need to go on 1. And the estimation is exactly the same estimated data type, standard error, fixed, and let's say R square within shows how well the variables without the variable expand upon. And one more thing that you should, let's say, keep in mind that the dummy variable regression in general will yield a very high R square, right? Because it does not abstract from the explanatory power of the dummy variable. So we should be very careful with that. Increasing in this case, when R square increase, it might not reflect the true, let's say, effect of our model, right? Let's say here, for t equal to most estimation, the fixed effect and the first difference lead to identical results. But when we have like more than 2, that means t greater than or equal to 3, the estimators are not identical, right? Fixed effects and dummy variables are always identical. Basically, the mean and the dummy approach are the same, but first difference and fixed effect will be different if we have more than 2 time periods, right? But again, if we assume that when n is becoming larger and we could apply the central limit theorem and the law of large number, both the first effect and the first difference, fixed effects and the first difference, they are unbiased and consistent. Anyway, that the assumption here is super strict because we assume strict exogeneity, right? And as a rule of thumb, you see that in papers where we use fixed effect or dummy estimator is the most common way the authors have been using, right? And if the UIT is uncorrected over time, so our error terms are uncorrected, the fixed effects estimator is more efficient. More efficient means it has smaller variance. But if our UIT, right, follows a random walk, basically the value of today is the value of yesterday plus some error term, right? And VIT, the error here is the white noise. That means when there is strong autocorrelation, the estimation in first difference is much more powerful or is preferable. But all in all, in general, using the dummy estimator in real life, in practice, are more preferred, right? And how about fixed effects with large t? We have to be careful when we use the fixed effect estimator, right? Especially if t is greater than n. Then if we have like large t, then maybe using the first difference is much better, right? Maybe now let's have a look at it's quite intuitive, so I will jump to the IB. But again, for the IB, I think we cover lots of like we analyze that from different angles and try to argue. It's more about arguing why the IB works, right? So I will also just try to find any theoretical points I should show you. Yes, exogeneity or relevant, we learned about that, right? But if we want to write like in formal terms, then relevant means X has an Z, right? The instrument has an effect on X. So covariance should be 0. But if instrument affect our Y through and only through X, right? That means now the instrument, the covariance of the instrument and the error term right? It's just another way to write down what we mean by our two conditions. So again, exogeneity could not be fully tested, right? But for condition 2, for relevance, we could test by looking at the first stage, regression. What do we look for so that we are sure to some extent we have a good instrument? The first stage F statistic must be greater than 10, right? For the case of 1 IV, and the coefficient of our, when we regress, Z on X should be statistically significant, right? Okay. Then I'll just explain extra and I will give you a few cases to think about it, right? And let's say if we have the OLS regression, it shows significant, statistically significant, but when we apply IV, it becomes not significant, right? Then what can we conclude about this one? So probably, like, assuming that we have a good instrument, right? Then we cannot say that there is an effect, right? So probably the real effect is not there, it's insignificant, and OLS is already inflated or it is spurious. It just shows us some spurious effect. Yeah. Here I'm just trying to derive the IV estimator for you for the case of one regressor and one instrument to see the relationship between our IV estimator, right? So for example here, our IV estimator could be written as the covariance of Z and Y divided by covariance of Z and X. And remember, if the effect of Z on X is very small, let's say 0.000 something, right? In other words, the instrument could not extract large amount of variation in X. Then if it's in the denominator, what happens if we divide something by a very small number or almost zero? It will become super large, right? If it's zero, then you could not divide at all. But if it's 0.0009, then our beta IV will explode, right? That's what we covered in class. Very good. And so let's say what is the difference between the two? So beta OLS is covariance of Y and X divided by X. But in this case, we simply replace X by Z, right? So now no more covariance between Y and X, but now Y and Z. And below, instead of covariance of X and X, right? Which is the variance, right? Here, covariance of X and Z, right? I just try to write down what it means formally for you. And for the case of weak instrument, we will suffer the consequence that we have high standard errors and we have bias or inconsistency of our estimator, right? And when we use IV, relying on hardware to judge if our variable is good or not might not be, let's say, recommended, right? It's not recommended to do that. And for the case of more than one instrument, so we could choose the best, right? Ideally, we could choose the best linear combination of all valid instruments, or we could conduct a test to see if our, like, among that set of instrument, what is the best, right? And here, when we have several inertial stage for each endogenous variable. So for example, if we have x1 and x2, that are the two, where are they here? No, right here. But let's say now the first stage, we have to regret the instrument on, we need to replace the first endogenous variable on each instrument, and the second endogenous variable on each instrument. We compute two predicted value and plug that in the second stage, right? That's how we're gonna do with multiple instruments or multiple endogenous variable. I also have some tests for IB, right? And these are the random slides, so maybe I'll just give it to you, check it at home. And also, I think it's helpful if you read the example to understand the context, right? Later, those papers are very seminal and they're classical. They could serve as a benchmark that help you, let's say, read or critically analyze the paper, the incoming papers that you might come with when you write your, let's say, master thesis, right? Okay. So we have economic interpretation, so it's also quite straightforward. You could read that at home. Okay, so we have those. And in this case, I mentioned about the difference in difference, right? We use the natural experiments or quasi experiment, right? Quasi experiment is the experiment that was not designed by the researcher, but by nature, something out of control or some exogenous event happening and no one could predict that, right? And it should be exogenous. Remember the shock of Lehman's collapse yesterday? And we have treatment group and control group. And at some point during the regression, during the paper presentation, I talk about the random assignment, right? So basically, the people who are in the treated and the people who are in the control group are selected very random. So they get remember the case where it says they got the ticket, right, to be vaccinated or not. That shouldn't be because how to say, I live in certain district, I will be prioritized to get certain level of less or maybe higher dose of the vaccine, right? If that's the case, then we will have bias. And what is that? What is the next assumption? In the absence of the treatment, both groups, control and treatment, will behave similarly over time. And that's why we have the parallel trend, right? The treatment will behave exactly like the control in the absence of the policy. So here, this is another way that we try to draft or visualize the difference in difference, right? I will talk explicitly about this one. So in the paper from let's say this one is from English paper, right? Okay, so let's say in this example we have South Carolina and North Carolina between let's say before and after one policy change in North Carolina. So basically now the North Carolina is affected, right? Not the South. So North Carolina is the treatment group and South Carolina is the control group, right? And we have the data. How do we visualize our coefficient here. So again, B2 is period 2, right? And BT is treatment. That is 1 if it is North Carolina and 0 if it's South Carolina, right? And the interaction term. And how do we interpret our beta 1 plus D1, beta 1 here, and delta 1, right? That is the difference between the treatment and control in period 2, right? And beta 0 plus delta 0 is the average value of our control group in period 2. And B0 is the change from period 1 to period 2, right? And how about the change in period 1 and 2 for one specific group, that is our treatment? So treatment is 1, BT is 1, BT is 1 here, right? Therefore, we have, so B0 plus B1 is the change in period 1 and 2 for treatment, and all four coefficients are the average value of T of treatment in period 2. And so to visualize that, we have beta 0 belong to the control group, right? So here, this is our beta 0, and the difference, beta 1, is actually the difference between treatment and control before the treatment, right, in T1. So we have to add up beta 1 to obtain treatment from the control group. From here, we jump to here by adding beta 1, right? And next, here in the control, so we have, if there is no so here, like D0, right, is our, delta 0 here is the value for the difference between this one and this line and this line is for the control group, and it's just the difference before and after, right, the policy. And here, delta 0, B0 plus B1 is the difference for the treatment group, because we explicitly look at the two lines above, right? B0 plus B1 here. And actually, the difference here is what we obtain, right? What we capture, what we could see in actual data. But the true effect between treatment and control is this line, the dashed line and the red line here. That is D1. DD will measure for us. So maybe you spend some time and won't think about that and ask me if you have any questions. But again, this is very much, let's say, illustrative, right? And we try to visualize the parallel trend or our pressure. I think basically I do try to have some detailed explanation for that, for the coefficient. Yeah, and here the motivation, the identification, we have to always assume that in the absence of the treatment would have evolved in the same way of the control group, right? To make this one work, right? Treatment and control group may differ, but all the important differences are assumed, are by assumption captured by our fixed effect. That is our treatment domain, right? And what we could do is to think about the treatment as not as one time, but it's a time vary policy, right? Let's say drum race tariff and the intensity, how close I am, how close we are to the treatment may lead to higher intensity. And by doing that, we could measure, let's say, the effect in granular level, right? Just further, let's say, expansion. So I think basically that's it. That's what I want to show you briefly in terms of like theoretical representation of theoretical, let's say, derivation of the methods. But when we read the papers, when we analyze the paper, I hope that you got already detailed, careful intuition, right, of the methods. Okay, so I think we are in good pace and we are all, let's say, done for the content. So do you have any questions so far? Okay, then I would say that thank you very much for your, let's say, engagement, your presentation during the previous days, and we, as agreed, we will have Q&A session next Monday. The exact time I will write, but right now probably I plan to have it at around 10 a.m. Right now too early. We will have 10 a.m. until maybe 12, depending on what you want, like how long you want to stay. And we have one extra on a second Q&A that will take place on the 23rd, right, of February, right after that holiday. So hopefully I could